the further you get down into what you're optimizing, the harder it gets. Like if you're optimizing at the microsecond level, then any kind of fluctuation is very annoying to deal with.
Getting an understanding for where your bottlenecks are in multi-threaded programming is, I would say, almost impossible if you don't have a visual representation of it.
It's super important to understand what a program is doing over time, because it can often give you information like if function A and B are always called together or like in a certain pattern, then those kinds of patterns can often be exploited for performance.
All right, then let's begin. Hello everyone. Today we're gonna talk about profilers, and we should start with the introduction. We have Dennis and Ritesh. So let's start with Dennis. Can you tell us a little bit about yourself?
Sure. Hi, and thanks for bringing me on again. I'm Dennis Gustafsson. I've been working with games for the last 25 years or so. My journey has been a little bit, it started off in game tools, and then for the last 15 years I've been doing actual games. But I have a background in physics, but I also worked on a profiler actually called Dress Code that we'll probably get to in a minute. But yeah, that was pretty early in my career. I've been using profiling a lot. I'm a big I advocate profiling a lot using visual profilers, so it's something that's close to heart for me. And most recently, I've been mostly known for as the creator of Teardown, the PC and console game.
Now, Ritesh, you're joining for the first time, so you need to give us a proper introduction as well. Dennis is well known in this community and everybody loves him. Now it's your turn to tell about your projects and what do you do for a living as well.
Right, no pressure. Hi, so I'm Ritesh. Thanks for inviting me. It's actually the first time I'm ever doing any kind of podcast, interviews, whatever. So it's new to me. We mostly just sit in the background working on stuff and not really doing this kind of thing. So it's kind of fun to try it out. Like Dennis, I come from games, of course. It's I think it's fairly typical for people in the profiling and optimization space to at least have something to do with games at some point in their life. I started out in the original Xbox development era. Like my first company was, the first company I worked at, wasn't my company. The first company I worked at was to build a game for the original Xbox. Back when the Xbox the Xbox dev kit was like a G5 Macintosh instead of like an actual dev kit, which was pretty special to be like on the ground floor of launching a new console. I've spent most of my career in games in engine/tools development, also like Dennis, with a focus on performance and optimization, and just basically being one of the persons that, hey, the game is not running at 30 or 60 or whatever FPS. Now it's time to fix it. We have 1 month left.
You were saying that, or you were receiving these requests?
No, I was receiving that. Yeah, it's like in game development. In game dev, my career is like the companies can be split into two parts. It's like the companies that keep like track of performance during development, and the companies where it's like a surprise 3 weeks before shipping that the game doesn't actually run at the target frame rate, and now it's time to fix everything. The latter doesn't usually work out that well that often. But yeah, I worked on just different games at different companies for about 16, 17 years. And then in 2017, me and my business partner Jelle, well, business partner is just a friend and colleague, we decided it was time to build our own company. And one thing we always missed during our game development optimization careers was a profiler that we thought was really good. There are many profilers, and I'm sure we'll get into those later on. But we felt we had like our own unique take on it. So in 2017 we started the company, started building it, and in 2018 we launched it. And yeah, we've spent the 7 years since just working on that, iterating on it. We're still just the two of us, so it's we are both programmers, but when you're running a company like this, it's definitely a question of wearing many hats to keep everything going. But yeah, it's been a very fun ride. I like we have customers, users all over the place, different companies, different continents, and like by osmosis, we like sort of pick up like what people are using Superluminal for and what kind of issues they're running into. So it's always pretty fun to get like a slight peek behind the curtain of like what's happening at giant companies that are working on, you know, big titles that people are anticipating, and just seeing that they struggle with performance issues just like everybody else does, and it's it's fun.
If you would like to support this channel, you can become a member on Patreon. You will be granted access to a private Discord channel where you can chat with other supporters and guests of this show. For more details, check out my website at łuka.sh. Łukasz.
It's nice that you can like help them actually bring out the vision and deliver the project, you know.
Yeah, we're of course only like a very small part of it. Like you know, especially nowadays, the game productions are giant productions with many people. But still, it's fun to be a small part.
Okay,
of it.
Awesome. Now, Dennis, you mentioned beforehand that you're happy to give a little bit of a history talk on the instrumentation. By the way, my state of knowledge is like instrumentation-based profilers, meaning I need to do manual work and annotate my source code. And then sampling profilers, they do it, they sample the process through question mark, whatever, I don't know. And that's it. Like, I have zero knowledge about profilers now, and I did this on purpose to act as a dummy now, and then just ask all sorts of questions. So if you can give a bit of a historical context, maybe, for the profilers, it would be awesome.
Yeah, that would be fun. I thought of different topics to talk about when you brought up profilers, and I came to think of when I grew up in the 80s and 90s. I was using a Commodore Amiga was the machine that I used to really learn and get into programming. I was programming assembly on them. And it just struck me, and I thought about this throughout my career, that already back then, there was a way of visual profiling that was pretty cool that I'm not sure everyone today who learns programming knows about. That could be a fun trivia. And that was the Amiga computer. You were very close to the hardware when you were developing, and it was using these CRT monitors. So the computer kind of worked in sync with the monitor, and the way a CRT monitor works is that there is an electron beam sweeping from the top part of the screen and is sweeping downwards 50 times a second if you're in the US, if you're in Europe. And if you're in the US, it was 60 times a second. It was kind of synchronized with the electricity system. And the way you could utilize that, since everything in the computer was memory mapped, you had basically a memory address that you could alter to change the palette, because this was a palletized system where you had something called bit planes, meaning that the hardware, when outputting the signal to the CRT monitor, it was reading from the palette and was reading these bit planes to figure out which color it was. So if you altered the palette, it was reading a different color. And that meant if you changed the palette while the electron beam was sweeping, drawing the picture, it would change. So if you do that like in the middle of the screen, the top half would be one color, and then the second half would be another color. And people very quickly used this to figure out that, but if I wait until I see the electron beam at the top, and then I change the color to something like, say, red, and I run my algorithm of whatever I want to profile, and then when that is done, I change it back to black, the height of that is going to be the time that it takes, because computers back then, there were no like power management, no changing the clock frequency of the CPU or anything. It was very, very predictable. So that was my first connection to profiling, or visual profiling, I should say. It was super low overhead because all you had to do was write a number into a register in the hardware. And that was basically just a few clock cycles. And then you do the same thing when you exit the algorithm, and then you could measure the time just by visually inspecting this bar of color that's on the screen. And you could, of course, stack these together. So it was pretty common back then, if you had a game, you would see you have different colors for different things. So say maybe audio was green, physics was red, and graphics was blue, and you did these things, and you could have like a visual profiler by just inspecting these bars on the background color.
So you had so you had like a vertical bar, and they would be like, some part is green, some part is blue, and you can see visually, meaning like the bigger the part is the one that takes more time. And
Exactly. And you usually, when pointing out to your friends, because all of us had roughly the same size monitor, when you said like, oh, I could optimize the physics, now it's only this much, and you held up your fingers and showed like so that was my first contact with visual profilers that I thought was really cool, and that really actually holds up today, even in terms of overhead and all that. And then from then on, moving over to PCs, it was pretty common at the time, or the time following the 90s and early 2000s, to just measure clock cycles. PCs at that time were still pretty predictable in terms of performance. There wasn't a whole lot of power management features back then. That came later. So just counting cycles gave a pretty accurate reading of how long something took. And it's actually an era that I kind of miss a little bit, because today, which we're coming to, it's all over the place. It's like so hard to figure out how long something actually takes, because the computer does all it can to try to stop you from reading the actual numbers and cycles that it's using to compute something. And then if we go forward a few years, we'd have dual core machines, which also has a funny story, because when they first came, and if I remember this correctly, I'm not exactly sure the order of events here, but I think dual core came around the same time they started to change, have dynamic clock frequencies. That was mid 2000s maybe. And I remember figuring this out when I had my first dual core machine. My profile suddenly started to show negative numbers occasionally.
Yeah. Going back in time, I remember.
Because the crystals on the dual core machine, they were not synchronized. So when you read clock frequency, because this standard for measuring things was still measuring cycles, and the cycle counters, they were running like almost equally fast, but not exactly. So it could happen that as your algorithm starts on one core, and then the operating system swaps something in and swaps your process out, and then this gets swapped back in again, or it moves to a different core, you would have another cycle count on that core. And that made it very difficult to measure performance using cycles. So there was kind of a rough period for measuring performance around that time, because you couldn't really do it. You had to fall back to the built-in timers, which had terrible overhead, and it was pretty hard. It was also around this time that Intel and AMD started both introducing these. There was something called Intel Speed Step. AMD had something similar. I don't remember the name, but the idea that you dynamically adjust the clock frequency, which of course made this cycle counter getting out of sync much worse. So it was basically unusable after that. And then a few years later, hardware people finally figured out we need some way to do this properly, and that's when the invariant timestamp counters started appearing in the cores, and that's really when measuring performance started working again. And I think that's been the standard since what could it be, 2007, 8, somewhere around. It was pretty close in time to when dress code. When I started working on dress code, I think it was mostly a coincidence, but it's probably not just. It's also more profilers starting to show up around that time, and there's a good reason for it, because it wasn't really possible in the years before it. It was possible 10 years before it, but not like 5 years before
for like
that.
Almost a decade, there was no good way of measuring.
I wouldn't say it was
much?
a decade. It was maybe a few years where dual core and these dynamic frequencies came around until the invariant TSC came. That was, but it was a relatively short period of just a few years, as I remember it. I might very well remember it wrong, but I think it was just a few years.
And Ritesh, do you have anything to add on top of that? Do you remember some stories from your time?
No, I'm just reminiscing in my head because I went through the same period that Dennis went through. I didn't start on the Amiga myself, but I do remember the RDTSCs suddenly returning negative time values during the early 2000s, which was like, yeah, okay, so I'm building a profiler and it's going back in time now, and how do you deal with it? Yeah, like, okay, let's just discard everything that's negative and hope it works out. But it was painful. Then, like, at some point, Query Performance Counter started returning sane values again, because I think Microsoft did something to get like an accurate clock even before like the invariant time counters were introduced, because they were like, yeah, it's not great to have like a time source that is unreliable on your system in general. And I do remember that. I do think, like, when it comes to profiling, it's kind of interesting to get into not to get into, but like to the distinction between sampling and instrumentation really comes into play there, because for instrumenting profilers, like Dennis is probably, I've never used Dresscode, but I'm guessing it was an instrumenting profiler. For those profilers, it's really important that you can get a timestamp that goes forward in time. For sampling profilers, it doesn't really matter that much, because you just take a sample at a point in time, and like afterwards you just sort all your events, and it doesn't really matter like what the exact order was, because it's all splattered together into like a tree anyway. So the actual timestamps were not that important for sampling profilers. So I didn't really run into it that hard, because during that period I was mostly using sampling profilers when I needed to. So it's kind of interesting to like see the different experiences from the same period.
RDTSC is a instruction that you can, like a machine instruction that you can get from the processor that will return a number of clock cycles that have passed for a given core, right?
Yeah, it's the number of cycles that have passed. Yeah.
And the invariant timestamp counter, what is that?
Today, it's actually the same thing. You do read it with the RDTSC instruction. It's just that nowadays that returns the invariant number, whereas in those days it returned the core specific cycle counter.
Okay, so there is some level of synchronization at the level of a CPU to give you back a sensible number.
Yeah, since they introduced that, it's all been pretty good actually, because it's fast and it's reliable and it's synchronized across the cores, and it has very low overhead. But it was something, I'm not sure how they did it, but it's something they added at the hardware level. So it's something that couldn't really be done. And not even today, I think all CPUs don't have it. You have to query that capability. So the way you do it is you ask the CPU, like, do you have invariant TSC? There is some bit somewhere indicating that. And if it says yes, you can count on that. If it says no, you have to use some other way of measuring time, basically.
Yeah.
Okay. And Dress Code, the first profiler that you wrote, was instrumentation based. Was there were there one type of profiler is popular in a given historical context before, and now it's switched to sampling? Like, how does it look like?
I remember using sampling some in the past. I also use it today at times, but I've always preferred instrumentation based, mostly because, as I said, my history with the Amiga and like how I was used to just putting markers in my code and getting that timing. I don't know. Do you know, Ritesh, what was more common back then?
I think back then, at least in my recollection, the profiling tools were generally not very great. So people would just use like basically sampling and instrumentation all together just to get like sensible data of, hey, what is my game doing per frame? I think back then and up until very recently, when you use a sampling profiler, typically what happens is, you collect samples, and all the samples have a call stack, and the call stack is put into a giant graph, and that's a call graph. And the problem with that, at least in the context of games, is that you lose like any kind of resolution with like time. Like, for example, if you're capturing the way a level is played, and there's a spiky frame in a sampling profiler, that spiky frame is entirely gone, because it's just all collapsed together into one tree. So you can't really see like, hey, this function in that spiky frame that took 50 milliseconds was like responsible for that frame. So for games specifically, I think people were mostly using asymmetric profilers because it was the only way that you could get like frame level information, instead of just I captured 1 second of data and I have like 100 frames in there, and like I don't know which frame was expensive, which one was cheap, which one is one I should focus on. So I think, at least in games, instrumenting profilers have always been the more popular one, simply because of that aspect.
And I think
at least, yeah.
I think people for a long time have used instrumented profiling, but presented it more as kind of just a single digit, or like a bar that constantly moves. Like, you don't really record the history and go back and inspect it the way we do today with instrumenting or profilers. So it was more, the first I remember doing that was actually, you brought up the Xbox One. Microsoft had a tool called Pix. It's probably still around. I haven't used it for a long time, but I think
it's not the same thing as it was back then. That one was really cool.
That was the first. I didn't use it myself, but I heard afterwards that used this kind of timeline idea. I don't know if it was for the GPU or the CPU, because I think they had profiling for both. But that's one of the first I remember.
I don't recall the CPU profiler for Xbox at least having any kind of timeline.
Okay, maybe it was only the GPU.
It was just a sampling profiler. I haven't really done much on the GPU side of things with profiling, so that's not really my.
That's on my list for questions for later, once we're done with the CPU. So Ritesh, can you tell me a little bit how a sampling profiler works? Where does the information come from? When I'm having a process, like, what do I have at my disposal to as an API to ask for how another process is doing? How does it work in general?
Yeah, so the basic functioning of sampling profilers, but also of instrumenting profilers, is all quite simple. For a sampling profiler, you simply have a process that can be an external process that simply passes every single thread on the system that is running, and then just asks the thread for what is your call stack, and then it just records that. So let's say that you do that every 2 seconds, for example. That's very high, very low resolution, but let's say. Then every 2 seconds, you know exactly what each thread was doing at that point in time. That's really basically all there's to it, because at every sample you collect the call stack at that point, and you just split all of those together, and that gives you a call graph, which basically is like function A called function B called function C, and like, the total time was 5 seconds, and 2 of those seconds was in function B, and 1 second was in function C, and that gives you like sort of a distribution that you can see, at the top there's always main, which is like 100% of your time, and then as you go further down,
the inverse
like the time breaks down into
kind of thing.
Yeah. So you start at the root, and you go towards the leaves where time just starts being broken down into smaller and smaller functions until you end up at, like the instruction level timings where you can see, okay, this function is like my hot function, and it's spending all the time in these few instructions or whatever.
But this is then the thread needs to be stopped for that. Yeah. Which means like it heavily impacts the performance of a running program.
It can. It depends a bit on like what you're using. So for example, in Superluminal we're using event tracing for Windows, which is a Windows built-in system that can be used to collect sampling information, and it can run at a maximum frequency on Windows at least of about 8 kilohertz. It's a little bit high. It's like 8192 or something. It's probably some kind of primer or something to prevent it from aliasing, but it's a pretty high number. And the advantage that has over like user space sampling is that it doesn't interrupt every thread. It interrupts the CPU that's running. So if you're if you have a machine with 64 CPUs, you just interrupt every single CPU and then ask it which process/thread is running on it and what's the cost tag for it. Versus if you have a user space sampling, something like Sleepy or Very Sleepy you might be familiar with, that actually just has to iterate through all processes on your system, all threads on the system, and then pause it, and then collect the stack, and then continue it. So of course there's more overhead involved there, yeah, for sure.
So when you set up event tracing for Windows and let it run at 8,000 hertz, you don't really do much in the app at that point, or you do need to collect the data, of course. But I see.
Yeah,
cool.
It's just collecting data. Yeah. Like it is possible to get the event stream real time and then display something in the app, but I've never really seen like the point of it in the sense that if you're profiling a game and like your frames are flashing by, there's nothing really you can do like at that point to like investigate the performance. In my experience, I know and have known people that do work like that. Like they see their frame flashing by, and like when they see a hot frame, they like press pause and then they scroll back a few frames and look at it. I've never really worked like that. So at least in Superluminal's case and most sampling profilers, they just collect data and then have like an offline phase that analyzes the data and processes it into whatever.
And then on the other side, because by the way, for me, my internet brain is like binary. You're either in one camp or you're in the other camp, and ideally those camps need to fight. Like there's like one tribe and another tribe. Like this is how I view this. So the instrumentation-based profilers, you need to every now and then. No, you say in your code where you want to start the tracing. And then the end blocks as well, and then you collect this in code, right? And then you have it sort of visualized. Is this how it works?
Yeah. I mean, maybe Dennis can speak to that since he is more experienced building arithmetic profilers.
It's very simple. You just take a timestamp when you enter something, and then you take a timestamp when you leave something. And on top of the timestamp, you also need the thread ID. And with those two things, that's really all you need to build these timelines, because then if you can trust the timestamp, which you nowadays can, you will always get them in order. So if something has a timestamp in between two other timestamps, that is a child of that timestamp. So that helps when sorting them, so to speak. And you typically do this, or I do it at least usually, if you use C++, it's very convenient to make this as a scope variable. So you put it on top of a function, for instance, and then when that destructor gets cleaned out, it does the second timestamp and puts it in some stream. And when it comes to performance and overhead, taking the actual timestamp is relatively cheap. What's usually takes more time, or what can take more time, is having some efficient way of storing and getting away with them.
Yeah. So these captures samples in both cases, they're huge, right? Like I used Superluminal for I tried to profile 60 seconds of like a startup of application, and it was reaching to 1 GB of capture size because of that. And like obviously it was like ton of stuff and the callbacks, like ton of libraries and everything, but the size of the captures is problematic at some point.
I think maybe it's different for sampling profilers. For instrumenting profilers, it obviously depends on how many zones you add and you use to instrument your code. In my experience, it's usually not that many necessary. My only experience is with games, but say I typically have a few hundred to maybe a few thousand per frame, something like that. And you typically only have like 8 bytes for the timestamp and maybe 4 bytes for the thread ID or something like that. So it's not a whole lot of data in my case. It's usually not something I think about a lot.
Yeah, it's different for sampling profilers for sure. It's by the way, to like slightly go back towards your question for now, you asked about the overhead of sampling and didn't really answer it. It's there is of course overhead involved with sampling, but the sort of advantage it has is because you interrupt every CPU at the same time, which means the overhead is how do you call it? It's evenly distributed. So, like, suppose that your program gets like slightly slower, every single function gets slightly slower. It's not like some part of the program are impacted more than other parts, because it doesn't really matter what code is running. It's just that when you take the sample, everything scales basically. So even if the sampling profiler slightly skews your results, it skews everything by the same amount, approximately. Of course, like there will obviously be some kind of noise in there, but that means that even if the exact timings are not exactly what they were in like real life, the relative timings are still the same, so you can still use it to make decisions about, okay, where is my time going? And compared to an instrumenting profiler, where, as Dennis said, you have to mark the start and end of everything, which means that like the finer grained your zones become, the more impact the performance has. Like, for example, if you have some kind of tight loop where you're inserting zones, then that really could explode the runtime of your program, because that loop that normally takes 1 millisecond now takes 5 or 10 milliseconds, because it has to spend all its time outputting zones basically. So that's kind of like a trade-off between those two things. But yeah, to get back to the current question, the data rate is definitely a thing. Because compared to an instrumenting profiler, a sampling profiler needs to collect a call stack, which is, nowadays everybody is on 64-bit. So each frame is 8 bytes. So if you take like a typical program that might have something between like 32 or 64 stack frames deep, like where it's commonly doing stuff, like if you run on Windows, the first maybe 10-15 frames already are just Windows CRT startup and call base thread tongue, and then call main, and then call some kind of CRT function before you even land in your application. So call stacks tend to get pretty deep. So if your call stack is like 64 frames deep on average with 8 bytes per frame, that's it's about 512 bytes per stack. And then if you're sampling at 8 kilohertz like we are doing, it's about 4 megabytes per second of data per thread, per CPU really. And then if you're nowadays, people are like 64 or 128 core CPUs. So if they're all like busy, you're just generating like, I don't know, about 200, 300, 400 megabytes of data every second if they're busy. So sampling captures get big very fast, yeah. For sure, and that is a problem.
Do any form of compression at that point? I mean, as you said, if there is like 20, 30 frames that's always the same, could you just say like, oh, this seems like it's the same as last frame, maybe I shouldn't save the whole thing, maybe I just put some marker in there?
Or that could be done, but it's like kind of it's as always in programming, it's a bit of a trade-off between speed and performance. Like as soon as you start doing that kind of stuff where you're comparing, incoming stacks with previous stacks and compressing it, that costs time at run, like during capture, and that time is not going towards the program that you're profiling. So in our case, what we generally try to do is just do as little as possible during capturing and just accept that there will be many gigabytes of data, and then resolve that during capture import time, basically.
You still do a terrific job, by the way, for sifting through the bytes in Superluminal. I've used it, and just like,
thanks.
I expected this to be way slower, to be honest, and then like it worked out of the box.
Yeah, it's that's not something that happens by accident. I think one thing with Superluminal, and that's where Superluminal start to differ from other profilers in general, is that other profilers typically tend to assume or keep everything in memory. So if you have a capture of a few seconds or whatever, and it's 4 gigabytes of data, then when you open that capture, the program it's just going to load 4 gigabytes of data into memory, and then if you have enough memory, then maybe it'll work. But if you don't, it will very definitely crash or go out of memory. When I worked at Gorilla, which was previous to starting as Superluminal, I worked at Gorilla, and one of the things they were doing there was they had like this data builder processes which would run on a server with I don't even remember like how many cores, but these were processes that would take hours to complete, and they wanted to profile it, and like there was not a single profiler that could capture like the entire process of a few hours long and then actually visualize the data in any way. And they built their own stuff for that, which was also based on instrumentation. But one of the things when we started Superluminal, we were like, okay, it should just be possible to capture like an hour of data, and it should just work, and everything should work no matter like whether you have 64 gigabytes of memory in your PC or not. So the fundamental difference that Superluminal takes versus other sampling and I think in general instrumentation profiler is that everything is built kind of like a game engine around streaming. So the entire set of data is never in memory at the same time, which sounds pretty straightforward, but comes with a lot of complicated challenges in like, we have stuff like a call graph. I explained earlier where a normal sampling profiler just puts everything into a call graph, and that gives you a giant tree. But like building a giant tree and then loading it into memory is like, that's by definition a unbounded problem. So we basically don't want to have anything that is unbounded. So even stuff like our call graph is built around streaming, and it's very complicated. Like if you think about it, like a call graph is built by just putting samples in there. So what does it even mean to stream a call graph, right? It's quite hard. And also stuff like we have a find functionality where you can just press Ctrl F and search for a function. Normally we just like for each bar in your profile, see if it matches the filter criteria and then output it. But we can do that because it's not in memory. So everything is basically just on disk, and we stream stuff in as needed. And everything is done with like a upper bound of memory, an upper bound of time, which is, like you said, why we actually can open captures that are gigabytes of size without problems with it. I think the largest capture we've heard of, at least that one of our users has opened, was nearing 200 gigabytes of data, which was just a capture of hours long on some kind of data server with 128 cores. They were all just basically hammering the cores. And they were like, yeah, so I opened it and it worked perfectly fine. They were like, yeah, that's great. But yeah, that is something where Superluminal is different from other profilers, that because like the decision around whether everything is in memory or is not is a very fundamental decision. It's not possible to basically bolt streaming on top of like an existing profiler that assumes all its data is in memory. It's something you have to choose in the beginning, like as part of your architecture, and then you get to have the fun of it for the rest of the lifetime of the product.
So the data is being stored on disk and then on demand. Yeah. For example, when you search for
a function or you want to visualize something, you load it from disk. I'm assuming you have some sort of acceleration structures as well. Okay.
Yeah. So when a capture is open in Superluminal, then we first go to this processing phase where we basically build acceleration structures. But that's like a linear walk through the events in the capture, and that's only done once. And after that, it uses the acceleration structures to basically accelerate.
I was really impressed by the performance when I tried out Superluminal. Like everything was buttery smooth, like 60 frames per second. Really pleasant experience.
Thanks. Yeah. It's been a lot of effort to get it to that point.
Yeah, you mentioned that 2017 the work started, 2018 it was launched, and then here we are almost a decade later, and you're still working on the actual product, which is, it takes a lot of work to make it like run that smooth and fast.
I mean, it does take a lot of work, but it's not like we spent 8 years just optimizing it. It's we have many users, and they all have feature requests and stuff that they want to have, and we want to do all of it, but we're just still two people, so it's basically we just do stuff as fast as we can, in like an order that we think makes the most sense given the often conflicting feature requests, and so we've just basically been just building out the profiler for the past 8 years.
Since we're on the Superluminal topic anyway, do you want to maybe highlight some of the features that Superluminal has that other profilers don't, or generally speaking that are well made in Superluminal?
Yeah, sure. It's so I think the major feature, at least when we launched, which was I think the major innovation we had, was as Dennis mentioned, even going back to the Amiga times, like having a visual representation of like what your program is doing on a walk log timeline is super important for performance. I actually watched your recent talk around optimizing the physics stuff, which was
thank you.
A great talk, by the way. And like one of the very first things that you mentioned in the presentation is like, here's like the timeline of what my game is doing over time, and you should have this timeline in your game, or at least at least somewhere, right? Because it's super important to understand what a program is doing over time, because it can often give you information like if function A and B are always called together, or like in a certain pattern, then those kinds of patterns can often be exploited for performance. But a sampling profiler doesn't have the timeline. In general, they just have a call graph, which is like, this is the graph of functions that are called over time, and it basically throws away the entire time dimension of the data. And we always used we ourselves also used instrumenting profilers in the past for reasons I mentioned earlier around like the frame timings, but generally the reason you use an instrumenting profiler is you want to have that timeline, and sampling profilers just didn't do that. So when we started Superluminal, we were like, okay, why is it not possible to just build a timeline based on the sampling information? Like it's already giving you points in time where you know what's happening. So why can't you just glue them together and then just reconstruct like what the program is doing over time? It requires a high sampling frame rate, because if you're sampling every 2 seconds, then that's not really gonna give you any kind of actionable timeline. But if you're sampling at 8 kilohertz, so that's about 0.11221 milliseconds, so 122 microseconds, then you can build a pretty accurate timeline of what your program is doing over time. And so in Superluminal, when you make a capture, you get like a list of all threads, and you can expand each thread, and then per thread you get like an entire timeline similar to what you will get in an instrumenting profiler, but without having to go through and mark up all your code and like, okay, this function is called here, this function is called there. And I think that is really the major thing that we introduced, that people were like, wait, this is so obvious, like why wasn't this done before? And now that I have it, I don't know how I ever did without it. So that's I think really cool, because it's one issue I've always had with instrumenting profiler is that if you have to mark up all your code, and like at some point, you output the data and you get like this timeline, like Dennis was showing in the presentation, and then like there's this gap where there's nothing, and then you're like, what is happening there? Does it mean that my function is slow, or does it mean like something is being called there that I haven't instrumented yet, or is it like some kind of combination between those things? And then what you often end up doing, especially like in large code bases, right? Because like if you have a code base of a game nowadays that is, I don't know how many millions of lines and abstraction layers and whatnot, it is very hard to ensure that you have like good coverage of all your functions to ensure that you get like a complete picture of what the program is doing over time. And even if you do have that, the overhead associated with instrumenting goes up because instrumenting vector pushback, for example, is just going to kill your performance probably. So there's like this sort of trade-off between, okay, I want to get like the full picture everything is doing, but I can't really instrument everything. And a sampling profiler has the advantage that because it's sampling, nothing can really hide. So on Windows, it's sampling on the CPU level. So even code that is not yours, if you're calling into some kind of third-party application or library, or on Windows because some kind of security software is injecting injecting a DLL into your process and it's taking up time during the file read or whatever, you can still see that happening. Even if you don't have the symbols for it, you can still see like, okay, hey, there's like antivirus.dll is injecting itself into my file read, and now my file read is very slow. So yeah, I think that part is just the major feature that Superluminal has compared to other sampling profilers.
I need to ask this. Is there, in my mind there is not, that's why I'm asking, is there any reason to use instrumentation-based profilers if you have a sampling profiler that can leverage the ETW on Windows, sample at 8,000 kilohertz, meaning 8,000 samples per second, which is quite a lot, and then see everything on a timeline?
I have an opinion on this, but
that's the part when we start to fight.
You're finally gonna have your argument, Ritesh.
Exactly, the debate. Blood.
Yeah. No, I can start, and for me, I think there are two dimensions to it. I would say this is probably individual also. I can certainly see the appeal of sampling profilers. I would say if you have a new code base that you want to learn quickly, if you switch projects a lot, or maybe you're a consultant working in different engines and want to get an understanding, sampling profilers would be definitely the better choice. But I think if you're working every day on a code base that you know very well and you want to get accurate readings, I do think instrumentation is the better choice, for me at least, because it gives a very accurate reading, and the work of instrumenting it, that's actually not a whole lot of work if it's a code base that you work with over the course of many years or even months, like just inserting this one line of code in the functions that are relevant to you. That's not really an argument against instrumentation in my mind. And I would say one of the things out of these two reasons that I was going to mention, one would be that an instrumented profiler is much more lightweight. It's something you can have always on. That's what I do for my engine. It's always sampling. I just basically can't run it in dev mode without also recording data. So if something happens, I just press F7, it pauses the program, brings up the profiler in the same process, in the same window, and I can just see the last, I think it's maybe 500 or 1,000 frames or something that I recorded data for, and see all the threads with very accurate readings. So getting this very lightweight, access to a very lightweight performance profiling data that's always on, that's something that's very valuable to me, because then I'm actually going to use it like every day for everything, and it's going to affect the work that I do. And the other dimension of it, I think, is the accuracy of the profiling. Because even if 8,000 sounds like a lot, if you run at 60 frames per second, that's like 130 maybe per frame, something like that. Whereas the things you want to measure, say, if you have your physics system taking out 10% of the frame time, you would only have like 13 readings in that. It wouldn't be enough to give like an accurate representation of all the things you do in that time. So I think at a high level, it would certainly help and get, especially for getting an understanding of the code base, but for doing detailed profilers or profiling, instrumentation, I think is the more accurate choice. And when it comes to overhead, well, we can talk about that separately, but it's really not so bad anymore. I would say. I know you had a point about that specifically, Łukasz, so we can wait with that until we get there.
Ritesh, do you want to respond?
Yeah, no, it's that's all very very sensible. I actually don't think I even disagree that much. It's
always with these debates, you know. I invite people like here's this camp, here's another camp. It's like, I actually agree.
Yeah, it's the way I always think about it in my head is like sort of as a bell curve, and that kind of goes back to Dennis's point about different dimensions. Is like if the x-axis is like the the complexity or like the well-knownness of the code base that you're working on, like on the left side, you know, there's people, they're writing like a new program, you know, they just typed in int main and like they're starting out optimizing it, whatever. The scope of that problem is so low that you could basically use sampling or like instrumentation and you would get your performance results either way. On the right side of the graph, you have people like Dennis who are working on a code base that they know very well, and they're optimizing it down to the microsecond level. At that level, you'll use stuff like instrumentation, but also stuff like ViewTune, which is, you know, where you're profiling like at the actual hardware counter level, where you're saying, okay, my physics system is hitting catch messages all over the place. Let's see if I can organize my data layout better, stuff like that. That's, I think, the area that Dennis is talking about, where you're working in a code base that you know very well, that is already quite well optimized, and that you're just basically pushing further. And like at that level, the accuracy of timings becomes more important than like towards the left of the graph. Then, in my mind, in the middle part of the graph is like, you know, you're a AAA studio and you have 300 people working on the code base on a game. Your engine is Unreal Engine or Unity or like your custom in-house engine, but either way it is a ginormous beast, and like nobody knows all the moving parts that are involved anymore, because it's just way too much to keep in one person's mind, because it's just, you know, you have physics and rendering and AI and navigation and I don't know what else anymore. And so in that kind of code base, whether you're new to it or like working on a day-to-day, like I mentioned earlier, getting the coverage for instrumentation is quite hard. But even if you're missing stuff, like I don't know Dennis's code base, but I'm going to assume that when he makes a change, it takes like a few seconds or something to get like back into the game, or like a very short period of time. In code bases like I'm talking about, it's like, okay, make a change, the compile takes 5 or 10 minutes. Getting back into the state where you actually had the performance problem takes 5 to 10 minutes, and by the time you get there, you've already forgotten what you were trying to profile in the first place. Having like that loop of, hey, I'm seeing something on my timeline, but the picture is not complete. Let me add markers and then try again. You know, if that's a loop that takes 10, 15, 20 minutes for each run, that's not something you're going to do that often. You're like, okay, you know, whatever. It's just I'll run something else. And so in my mind, like the middle part of it is code bases that either have not been instrumented yet, because, you know, nobody has cared about performance in the past, or you're new to it, or the coverage is not good enough, and they're a sampling profiler like Superluminal that has a timeline, not a sampling profiler that just gives you a call graph, because that is useless. But a profiler with a timeline is in my opinion, way more powerful, well, more useful, because you don't have to go through that process of doing it. I think in general, it's there's quite a lot of discussion nowadays around the performance and quality of software, and I'm often of the opinion that if people just profile the applications, like even once, they would just find stuff that is just there for the taking, because most programs are never profiled at all. So my and our point of view is that lowering the barrier where you can just without doing anything, just get performance data is the single most important thing that we try to do. So in our case, you download it, you run the application, you don't need any kind of modifications, you don't need to hook up an API or whatever, you just run it. Basically, like lowering the barrier that people can just even try to profile the applications is sort of our contribution to getting better performing programs out there, because it is to cry about nowadays. And honestly, people just profile, and I think if people just profiled, there are like easy 10 to 100 times the wins in there, because most programmers just don't profile, because they either don't know how, or the effort to go to actually getting valuable data out of it is too high for them to bother, because I'm working on some kind of task. I don't want to bother with setting up this API or whatever. But if you give them something that just gives them data immediately, even if it's not microsecond accurate, as Dennis is mentioning, is more valuable than having to instrument it, basically. That's kind of my take on it, and it's
a fair point. Yeah.
What do you think about that, Dennis?
No, you're right. I'm mostly used to pretty lean code bases that are easy to modify and easy to insert new instrumentation into. And I'm always surprised when talking to other teams and other people how they work, that it's not a whole lot of people using profiling on like a daily basis. That's something once in a while, maybe if you have a performance problem. But whereas I look at it like 10 times a day, like every time I find something, that's the thing telling you how good you did it. Yeah. So you want to keep an eye on it.
Yeah.
And I agree, people should use it more. And so I do think it's an important thing that you're doing at lowering the barrier to entry for that.
But this was exactly my experience. By the way, for a long time, I was programming in these like higher level languages and like ecosystems like Java, Python, and like something like that. And from a couple of months, I am working with C++ as a main thing. And like anything I touch is like, okay, now here's like a tutorial, 10 steps to do anything, And I expected profiling to be the same. And for a couple of profilers, I would not mention them by name, but like if you need to set it up, especially if it's like an instrumentation profiler. You would need to download it, and then you need to like call. So like there's like this step and that step. And with Superluminal, I like in 5 minutes, I was looking at the brand new like timeline of a program that is huge. I had no idea what it's doing, and I can see, here's the font initialization. It takes this much, and here's like some style sheets, and like this was like. Just for the program exploration, I think this is incredible. Yeah. Like most people with the huge projects, I am assuming they have no idea what is happening, because by the time they ship their thing in 2 weeks, implemented in 2 weeks, 300 people ship their things, and like everything is changed now. So the ability to even explore this during runtime with a profiler is awesome. And I need to shout out like the ease of use and ease of starting with Superluminal is incredible. Just like dump
that was amazing.
exe, boom.
Thanks. That's great to hear. We put in a lot of effort to basically get like a sort of it just works experience. Is something is what we always call it. We don't want to go like. On consoles, you have profilers that when they're also sampling profilers, and when you run it, you get like this dialogue of like, okay, here are like 5 billion options that you can all configure around the profile, and we're like, no, just here's the application, run it, and leave me alone. Like if I need more advanced stuff, I'll like find it later, but don't throw it in my face. So we've put a lot of effort into getting that barrier low. So it's great to hear that it kind of it comes across.
There are more
technical questions, but there's one sort of less technical that came up from the audience, which is, how should new programmers learn profiling? Like, what would you say in terms of like where you would find a profiler that is suitable, and how to sort of like understand yourself in the call graphs, or what to do?
Well, I guess downloading Superluminal would be a good first step because that would be super easy. And I think when it comes to instrumented profilers, there are a couple of instrumented profilers that are fairly easy to use, but nothing that comes close to that experience, I must say. I would actually highlight how easy it is to write your own instrumented profiler. Like it's literally taking, there is a Windows, if you don't want to deal with RDTSC and doing those intrinsics, there is a query performance counter API in the Windows that's really good. It's also very low overhead. It's using RDTSC internally. And then just putting them on a stream and visualizing that graphically, if you have some way of outputting like things on a line. That's not a lot of code. I actually looked just in preparation for this podcast how much the one I'm using is, and it's less than 1,000 lines of code, including collecting it, data, storing it, and drawing it. So it's not a lot of work. It's all pretty simple. And that includes all the threads and everything, so it's fairly easy. And it's also one of those things. It's also one of those things that you could do. You could start very easily by just displaying the last frame, and then maybe you record a couple of frames, and you can add the threads on top of that later. So it's something that you immediately get a big benefit of by just adding something, and then if you want more detail, you can just build on that incrementally. Yeah,
for sure. It's I think one thing you often see nowadays is what you mentioned earlier is people. If you think about an instrumented profiler, you take a timestamp, you take another timestamp, subtract them, and then you printf like the result, and basically that's an instrumented profiler. And like everything on top of it is just visualization and outputting. But one thing people often do when they start nowadays is they use their IMGUI, the GUI stuff, where they collect data using their take time, and then they just output it to the screen using IMGUI, and then just have like a graph where it's like, okay, render's taking 5 milliseconds, and 4 of that is in that, and like that is already very useful. I think, to go back to your question, I wonder whether people are asking, how do I start profiling, or how do I start optimizing? Because those are two different things that are related, but not the same thing. It's like optimizing the code that you have is very specific to whatever you're doing. It's hard to come up with like just multi-threaded or whatever. It is so context dependent. But for profiling, I personally wish that there was more resources around like how do I profile out there. It's to me, when I'm profiling, I'm always looking for patterns in like what's happening in my code base. Like I mentioned earlier, it's if you have some kind of frame loop and like every frame function A and B are like called together and work on almost the same data. That is like information that you can use to maybe we can pull out the calculation into like a higher level, and then have A and B share that kind of stuff. It's like understanding the context of every function, like not only that they are called, but when they are called, why they are called, and like what else they're calling. That is often very important to first understand, like analyze what is your program actually doing over time, and does it make sense for it to be doing that, right? If you have some kind of function that you expect is 2 milliseconds, but it's now 100 milliseconds, then zoom in on that, and they'll be like, oh yeah, well, I guess I have more objects now, and that's just what it is. And it's oftentimes I've noticed is that performance problems are almost never where you expect them to be. It's always like, oh wait, shit, I'm calling this function, and internally it does like this function call, and that function call results in like a vector, find or whatever, and that means that what I'm doing up here it actually turns into like this O(n) squared loop, because like some function further down the line is doing some kind of find that I wasn't aware of, and like looking at the call graph, looking at the source code, and understanding those relationships, and like I know this is very fake and non-actionable advice, but that's like the thing I personally always try to do, and it's actually one of the things that people, to go back to like sampling versus instrumentation. Like I do have a few spicy things there. It's quite a lot of our users used to be instrumenting profilers, like Dennis, and over time we've. Not often, but a few times we've had bug reports from Superluminal where they were like, "Hey, Superluminal is showing this, and it's impossible for it to be doing that because like I've measured it with my instrumenting profiler, and that doesn't happen." And then like they continue investigating, and they're like, "Oh wait, shit, Superluminal was completely right, and we actually are doing that." And and that's like kind of what I meant earlier with the sampling profiler, assuming the resolution is high enough, nothing can really hide because everything is just being sampled. And with instrumenting profilers, it can easily happen if you just forget to add some marker somewhere where your time is going somewhere. You're like, this doesn't make a lot of sense, but I guess this is probably fine. Like if there's like a big gap, then it's obviously spot. But oftentimes it's like there's this little 5, 6, 7, 8, 9, 10 microsecond gaps that you're like, yeah, that's probably just the CPU just doing some kind of calculation, which actually turns out to be is some function being called that is super fast when you call it one time, but not so fast when you call it 1,000 times, and then at some point that just explodes in performance. So that kind of turned into like this rambling rant around profiling. I don't really have an answer. Like, how do I profile?
You touched on something really cool.
Yeah.
Like, only when you start using profilers in general, you start to see how much time things take. And this is not like nowhere in the university you will like hear to do that. Like you will have zero expectations on how much a function call is expected to take. And then once you start to profile, you'll be like, why is this like 10 microseconds and this is like half a second and this is like 4 seconds? Because like that's also happening. And like, is this normal? Yeah. And then you start to dig deeper and deeper and sort of like lead yourself on this journey to an adventure to see what is happening, which is this happened to me multiple times. And like when I showed this to somebody, they're like, wow, like, yes, like that's my reaction when I've seen this, right? But like we have to do this more often, like use these tools to actually discover this, like to learn.
Yeah. I think in general it would just be good if people profile more. Like whether they're using sampling profilers or instrumenting profilers, I don't really care. Just profile and optimize your shit. It doesn't have to be hard, and like it comes with experience, right? Like neither Dennis nor I started with like, okay, yeah, we know exactly what's going on and we're going to optimize everything. It's just something that you learn over time, and it's the best way to do it is just by doing it.
I would like to add one thing also when it comes to multi-threaded programming. That if you're just measuring, I mean, some people do instrumented profiling very lightweight by just taking 2 samples, subtract and print the difference, or output to some spreadsheet or whatnot. But not having that visual representation where you line up the threads and see how they block and wait on each other. That's going to be getting an understanding for where your bottlenecks are in multi-threaded programming. Is, I would say, almost impossible if you don't have a visual representation of it. So that's where I think the timeline profilers, whether it's sampling or or instrument, it doesn't really matter as long as you have a visual representation over time. What's going on. That's the most important part, I think.
Yeah, I agree. I remember from your talk, like one of your conclusions was, you need to have like some kind of visualization around what your threads are doing to be able to understand performance nowadays, because nobody's running like a program that is a single core anymore. And like even on Windows, if you write a single threaded program, there are other cores and other processes on your system that are still doing stuff.
Right.
It's one thing about Superluminal is that it's a sampling profiler, but we also collect context switches and what Windows calls ready thread events. So basically, if you open it, then every thread, if you've used it, you've like seen like all the colors going on where it's green and red, and that's like all based on context switch information. So it's very exact. So as soon as you see like a thread that is colored not green, it's red or blue, like depending on like what's doing at that point of time, that means the thread is switched out. And you can inspect the cossack at that point to see why it switched out. And if you click on the block, then you get like an arrow saying like, hey, this thread was waiting on the mutex that this thread was releasing at that point in time. And I totally agree. Like understanding those kinds of thread related issues is very important. It's so easy to like okay, let me just put a lock here and then continue on with my programming and then think it's probably fine. And then you profile it and you see like, all threads go idle here and like this one thread continues. So basically you just have, single threading with multiple steps. And it's always very eye-opening to basically just make a capture and then see, okay, so I see like this, all threads are going idle here and this thread continues. And then like, and then like when it's done, then suddenly they all wake up, that's usually like this indication like, okay, something is up here. I should probably look at my synchronization or like my primitives or whatever to see if I can optimize it further. And I really liked your talk there where you were like, okay, let's try the spin loop. Let's try the lock-free algorithms and like seeing like the difference it makes. And that's what I meant earlier, where if you're optimizing at that level that you're at, where you're actually squeezing out microseconds, then instrumentation is probably more effective because sampling is just not going to give you microsecond level granularity. So that makes total sense. But it's for most people, they would just like Lucas was saying. Hukas, I think, sorry. You make a capture for the first time, you're like, okay, so during startup, we're spending 10 seconds reading in the file, hey? Let's see. Let's see whether we can do anything about that.
It's interesting that we call profilers, and then like the connotation is like, oh, now we're optimizing and like making things happen quickly. And for the past 15 minutes, we talk about like visual aid to understand your program. Right, like there's concepts that are missing from the name that like we all like.
It's a super important aspect of profilers that I think are not mentioned as much as they should be. I mean, that if I want to understand a new game engine or something, the first thing I would do is to either use Superluminal or put instrumentation in there to see what it's doing and like how do all the threads interact and in what order things are called and which part of the code call other parts and all that.
And I totally agree. It's like the humans have like evolved for vision. Our visual processing centers in the brains are very powerful. So being able to visually spot patterns, like doesn't matter whether it's instrumenting or sampling, but just having a timeline that shows you what's happening and everything visually makes much more sense than okay, here's Excel and there's like rows and tables and like columns of data, and have fun with it, because people are not good at spotting patterns in like numerical data like that, but they are very good at spotting visual patterns.
Now I have a technical question. How do you use hardware efficiently for a profiler? We started to touch a little bit on Superluminal design with having data on disk and then streaming it to memory only when you use it. In general, what is the hardware bottleneck? Meaning, is it disk? Is it CPU? Is it like
RAM. Like when you're building a profiler and you want it to be reliable and work in various situations, what would be the common issues? How do you use hardware efficiently?
I think that's mostly for Ritesh, because as I said, the one I'm using currently, at least, it's not really enough data to stress the memory or the disk. I just keep it in memory. One thing I do is I want the overhead when profiling to be as low as possible. So what I do is I very efficiently collect these timestamps and put them on an array that is pre-allocated. So there's no memory allocation or anything. And I do that, I have one array per thread. So there's no locking, there's no atomics, no anything. It's just keeping that array pointer in a thread local, and it can instantly just put stuff there without ever communicating with other threads. And then at the end of every frame, I do the heavy lifting, the going through all the zones, trying to figure out which was a child of which other zone and putting them hierarchical. And that's also a point where we differ, I think, because in your case with Superluminal, you do collect the whole session, and then at the end, you do process all that data to make it presentable. Whereas every frame, I do process that frame, and that also show up on the profilers. So, and it's not very heavy. It takes like, I don't know, maybe 0.1 milliseconds or something, because it's not that much data. So the processing is not really that much of a concern, or the hardware or using it efficiently. It's mostly when collecting the timestamps and putting them, storing them, that has to be very efficient. But other than that, I don't really have any special concerns.
Yeah, that makes sense. It's on our side. It's definitely a concern, but it's hard to say like, this is the most important hardware, because it just depends on what it's doing. So in our case, you have the capturing side of things, and Dennis earlier mentioned like can you do some kind of cleverness to basically compress text during capturing, and it's something we could do, but we want to get the capturing part as low overhead as possible. So on Windows, we haven't written the capturing backend ourselves, but we are currently working on a Linux version of it, and we are doing everything ourselves there with the capturing, and it's an absolute nightmare.
Why?
But it's that's way out of scope of like a profiling talk. But just supporting a caption backend on Linux that can collect at a high frequency is an absolute pain, because the main problem is that on Linux, for most distributions, the system libraries and basically just any kind of package that you're using are not compiled with frame pointers. So collecting like a backtrace involves quite a lot of work, which is work you don't want to be doing, because you're sampling and you want your overhead to be like as low as possible, and you don't want to be looking up stuff in maps and like in like any kind of lookup is just annoying. Don't really need to go into that, but like the general approach, like Dennis is saying, of having per CPU or per thread buffers that are thread local, and you just put your data in there, and then at some point you just flush everything out to disk. Without any kind of processing, basically just to get the overhead as low as possible is on the capturing side of things is very typical. That's what ETW does on Windows, Event Tracing for Windows, and it's also what we're doing on the Linux side. But when we open a capture, then you have stuff like, okay, I have a 180 gigabyte capture on disk, and you need to go through it at least once. That's unavoidable, because otherwise you could never show your data. So, doing that part, I/O of course is very important. So it's good to have like an idea of, how fast can you expect I/O to be, and then you have people tend to conflate I/O with, hey, it's doing something with reading stuff, and like actual waiting on the I/O of your drive. Like SSDs are very fast nowadays, especially NVMe drives that people tend to have in our audience with developers, I think. So when people say, yeah, I'm I/O bottlenecked, I'm also like, yeah, are you actually? Because because your NVMe is very fast, and most likely you're actually reading it very fast from disk, but then you're doing something with it to like get it in a state that you can actually do something with it. You're either decompressing it or you're processing it, and that's your bottleneck. It's not I/O. I/O is fast, usually, not always, but usually. So that's a bottleneck. And then as part of that process, we're building data acceleration structures, and that's all very memory heavy again, because then you're going through the data and generating new structures, and the structures will speed up lookups later on. But while you're building them, you're touching quite a lot of memory, because everything, you're going through your 180 gigabytes of data. So that all needs to be put into a qual graph, which is like, a tree of nodes, and you can do lots of cleverness around pool allocators and linear allocators and making sure like all the nodes are close in memory and whatnot. But in the end, you are building a qual graph that might be, you don't know how many levels deep with how many millions of nodes are in there. Like at some point, that is just the problem. That is just what it is. There's also stuff like we try to do stuff in parallel, of course. Talking about making use of the hardware, doing as much as possible in parallel. And we have kind of a similar problem that Dennis talked about in his presentation with physics, where calculating like the contact points is like pretty much it's a sequential problem, because it's like you can do cleverness like with the coloring that he explained to basically break it up. But in our case, because we're building a timeline and events arrive in order, you cannot process events out of order. So it's just process event, process event, process event, process event. That is a strictly sequential problem. So everything that you do in like per event processing immediately explodes like the entire runtime of like that first step. Because if you have a capture, that is, I don't know, a few seconds, then maybe you have like a million events, and you're like, okay, if it takes 1 milliseconds per event, it's fine, probably. Actually, no, it's not fine. But like if you do it like times 100 million events, because you capture for an hour, and now you're spending 1 millisecond per event to process it, then it's like, okay, good luck, waiting for that to finish ever, because it's just going to take hours and hours just to get through the file first before you can even visualize it. So there we spend a lot of time making sure that our per event processing is like as efficient as possible, and that is like an ongoing thing, because there's like the problem with making something that is scalable is that people tend to keep throwing bigger and bigger things at it. Like in the beginning, people were like, "Hey, I have a capture that is 4 gigabytes." We're like, "Oh, that's huge. Let's see if we can load this in." And now they're like, and now it's 10, and now it's 20, and now it's 30, and now it's 40, and now it's 50 gigabytes, and like that keeps going. So like your performance bottleneck just keeps moving. Basically, it's not really like a game where you can say, okay, now we're at 60 FPS, we're done. It's just we have hit like the current limit of performance, and tomorrow somebody else is going to like go over it, and then we have to figure something out there again. So it's very hard to say like, okay, this is the most important thing, because it's just depending on the capture that's being loaded in. It's
by design difficult to parallelize because it's in order, and basically it scales with the capture size. So the bigger the capture, the more time you need to wait for the processing anyway.
Yeah. There is just a scaling factor there that is unavoidable, because it's just it's ON and the N just keeps growing. So it's the only thing you have influence over is like how much time you spend per N, basically.
Okay. Now profiling GPU. Because we talked a lot about profiling CPU, and this is like sort of the main thing. And since this is somewhat related to game development, and lots of people here have a game development background, there's also a GPU, and it's way more obscure than CPU usually, and it's more difficult to understand what the hell is happening and whether it's actually efficient and how to collect information. What can you say about profiling GPU?
I can't say anything about it. I have zero experience on the GPU profiling side, so I hope Dennis can shed some light on that. I'd be very curious myself.
I also don't have a whole lot of experience. We do use it currently at work. We're using Vulkan, and in Vulkan you can get these timings back. You need to insert it when you upload your command stream, and then you can retrieve them. They are delayed a couple of frames, or some frame at least. But you basically get back the same thing. You get when it started and when it finished in between those markers. So we do put them also together with the CPU, so you can visualize them at the same time. It's not going to be reliable because the clocks are not synchronized between the GPU and the CPU, so you're not going to see exactly when it happened. And also since there is a delay of a couple of frames before you get them, you cannot, or you have to make like an offset to see which frame on the CPU that correlates with the frame on the GPU, because it's going to be 1 or 2 frames behind, or 3 even. But essentially, it's the same thing. I can't really say much more than that on what you can get from a GPU. I think when it comes to GPU, there are tools like NVIDIA Nsight, for instance, that does this, or RenderDoc, where you can get very detailed. In Nsight, you get a very similar timeline where you can see what all the parts of the GPU. You also get information about memory accesses, cache misses, and all that kind of stuff, which is really useful. But I don't really use that myself much, since I'm more of a CPU programmer than a GPU programmer. Yeah. So I don't have that much to add.
Yeah. So you're basically what you're describing is actually again an instrumented type profiler, right? Where you're instrumenting the GPU side of things actually, and then putting it onto your same timeline.
The thing that we use is instrumented, but if you take NVIDIA Nsight, for instance, it's actually well, I wouldn't say it's probably not sampled, but it's like automatically instrument. You don't have to insert that manually. It knows all the passes that you run on the GPU, so it can also collect that data.
Yeah, I do want to make a slight correction to your previous examples where you mentioned RenderDoc as a profiler.
I'm mixing it up. It's not.
Yeah. Like it's more a debugger, and I know people try to use it as a profiler sometimes, and I also know that Balder, who's the guy that works on it full time, hates it when people use it as a profiler because he's like, it's not a profiler. It's showing you the draw calls. It's you cannot rely on like the timings in there to basically give you any kind of indication of like what time your GPU is spending where. Basically, it's a debugger, not a profiler, which are related but different. Yeah. So I just wanted to slightly correct
established that we like profilers because they also help you understand what is happening. So with this, like, it's a huge overlap with RenderDoc in general, because like I used RenderDoc and I was amazed just by the sheer volume of information that you can get from a frame, like when you're running something, like what you can get back. I thought this is like lost, like it's out there, GPU, like zero ability to get anything back, and then you can make a capture and actually learn what is happening from the running process.
Yeah, it's super cool. Like I am not a GPU programmer at all, but we do our own custom rendering in Superluminal for the timeline to make sure it's at 60 FPS and everything. And RenderDoc has been invaluable in the past, where like, okay, my screen is black and I don't know why. you just open RenderDoc and it's like, oh yeah, this thing here is wrong or whatever. So it's very, very
to
cool.
be fair though, RenderDoc does give you the information that we like the second half of the profiler, like getting the understanding. but you're right, it's not measuring
that's
time.
True. Yeah. But the timings are not to be relied on basically.
Now we're entering the last phase of the podcast, and I would like to ask you about the future of profilers. Since you both spent a lot of time working on profilers, what do you think
can happen in the future, or should happen, or could happen in the profiler space? Meaning, what would be the nice improvements, or how do you see, or like some wild ideas how one can profile in the future, given that things can improve?
I can start. And I
Sure.
on top of my list would probably be some way of measuring more hardware counters. I know there are some hardware counters. I don't know exactly how to read them or how to get them. I think a lot of that is only available through kernel, like if you're closer to the kernel.
Yeah.
But if there was any way of
It's hard on
measuring,
Windows.
say, the number of cache misses in between these two markers, or branch mispredictions, machine clears, or memory, how much memory bandwidth was used in this zone, that would be super useful. And but it seems like we're not particularly close to that. From what I've come to understand, I haven't researched it that much, but it seems like you at the very least you would need to write your own kernel driver to do that, which seems clunky and not this lean experience you want with a profiler, really.
Yeah. It's I do know that ETW has some kind of support for capturing performance counters. It's all very undocumented, and like you have to know the right incantations in the API to like get the data out of there. But it is there, I believe. And ETW also has like this thing where they what do you call it? You can get events like in real time, so you don't have to actually output it to disk first, but can just start a tracing session and then consume events in real time. So you could potentially use that for your profiler, where you would just, I guess, take a mark at some point where you just ask ETW like, hey, what is your current status of this count or something? I don't really know, because I think like normally the way it works is like you have this counter and like it overflows every n events, and then like you can get an event like, hey, there was a cache miss here. And then in another 10,000 events, you get like another event, and then there's something going on there. But as far as I know, like ETW is the only way currently to get hardware counters, like you mentioned, without going like, hey, let's write my own kernel driver type thing, which is something that VTune and stuff are doing. But I have personally never been able to get VTune to work on any of the machines that I've worked on in my entire career. Like it always used to blue screen in some kind of kernel thing. So it's in my head, it's kind of like a here be dragons kind of area where it's like you can do it, but do you really want to?
It's also something I would be. I mean, just trying out the profiler, running it like Superluminal, that's really lean. But if it requires me to install a kernel driver, I would be like, this sounds like it could mess up my system.
Maybe
I probably don't want to try that. So
yeah, for sure.
There's a bit more resistance, I think, to trying it out.
I like how Ritesh said that you need a special incantation of the API. And before you showed up, somebody in the chat sent the link from Casey Muratori, his blog post titled "The Worst API Ever Made"
Worst API ever
on the
made.
event tracing for Windows, which was like some incantations.
It's a famous blog post, and I have to say I kind of disagree with it. In like the blog post make complete sense, and like the criticism in there make complete sense. But if you get down to it, it's a few function calls that have confusing parameters for sure. But once you have it running, it just runs. So it's not really something that I found bothers me a lot. But it definitely, like, the further you get into like weird details like hardware counters, then the more obscure it gets, because it's just all undocumented, and that's just figured out.
On the note of reading cache values and cache misses, there is a talk by Andreas Fredriksson, lead Insomniac, lead director for the engine at Insomniac. In 2017, they made open source the cache sim,
which is a simulator,
simulator,
that you can
it's
run through your program. It takes much longer to run, but it is like one-to-one what would happen on your CPU, and you can read all the values. It looks super cool.
Yeah. I know of the project. I haven't used it myself, but that kind of stuff is really cool. If you're like optimizing at that level, it's super awesome.
There's actually one more thing, if I can add,
of course,
that I came to think of, and you're probably familiar with this also, Ritesh, that now I mentioned the speed step and how difficult it became to get through cycle counters, and I think that it's that's something that's still very problematic. Like how do we set up the program to actually measure the performance? It sounds like it should be easy. Just run it and you measure, but it's not really like that, because especially for a game, if you use VSync, for instance, and you have the game wait for each vertical blank of the monitor, it's gonna and the CPU is not using that full 16 milliseconds or whatever your refresh rate is. It's gonna go idle for some time, and then that power save features are going to kick in and see that like this is actually not using the whole core. Maybe we can lower the frequency a little bit. And when it does that, it looks like the thing you're measuring takes longer than it actually would if it was more loaded. So you can never really trust the things you measure these days unless you know exactly what you're doing. And that's actually really hard. And it's getting worse because now we have P cores and E cores. And
you
can pin threads to certain cores. You can do warm-up passes where you like run things on the whole machine to make it like fully alert and stuff like that. But having some way to bypass that would be awesome. If there was like something in the OS say, hey, I'm gonna measure some performance now, don't do anything stupid, please. And then just let the machine run. It does, I can see that it would get very hot and stuff if you would run the whole thing, but it would be totally fine to run it at like 50% as long as it was super consistent. Like if it just ran at a fixed frequency. Maybe there is a way to do that in BIOS or something, but I don't really want to go in there and change that every time. Since I want this always on, it would be so nice to just have some setting for that.
Yeah, it's definitely an issue where it's like it's hard to know exactly what you're measuring for sure, especially on something like Windows. Like even leaving aside frequency boosting and changing and like cores going to idle and whatnot, it's just you're working on a OS that has other processes running. So you're like profiling your game or your application or whatever, and like Discord or whatever comes, it's like, hey, I need time now, and like takes up an entire core, and that is invisible to your process, right? And it's like those kinds of things can really mess with your measurements. It's the thing with frequency is I know that Windows, well, again ETW, they have events that are output like when a core switches frequency level or like enters an idle state and stuff like that you could potentially use to again display at least some kind of visual where like, hey, the CPU was downclocked to like half in like this part where your function is suddenly slower than you expected, so you can at least sort of correlate it with what's happening. But it would indeed be ideal if you could just say, hey, I'm now going to enter some kind of profiling session, please leave me alone, run at full speed.
Yeah, that would be really great.
But again, at the same time, if you're profiling your application or your game and it is triggering this kind of behavior, then that means that when you ship your game, it's going to trigger that kind of behavior on your user systems as well, and they won't have to ask you to say don't do that, but run at full speed. So in that sense, it is kind of a realistic representation of what would actually happen when you ship your game, probably, right? Even though it does make it quite hard to compare like numbers.
So at least when I'm using profiling the most is when I optimize something. I want to compare like this version of the algorithm to that version, if you can't really trust them. So typically what happens if you don't use the whole machine, it just looks like it actually took more research than it actually did. So in that sense, it is not really representative for what the end product is going to be.
Yeah, but this is more about like Windows running wild processes and taking up the CPU time, or is it more about like power optimization features where you want to save the battery for laptops and stuff like that?
Yeah, it's the power optimization, and that
it's just power.
That used to be more something you could dial and control more fine-grained. I think today there are so many things. There are two different things on a CPU. There's a P state and the C state, where the P state is it's basically the speed it's running on, the frequency, and the C state level is something when if a core is idle, it can basically go to sleep at a number of different levels. So it's running at something called C0 when it's actually doing stuff. And then if it hasn't done anything in a couple of microseconds, it goes into C1, and then it can drop deeper and deeper into like C2, 3, 4, 5, 6, 7, 8, 9. And the deeper it goes to sleep, the longer it takes to wake up. So
it's like REM cycles. It's like REM cycles in CPU.
Yeah, a little bit. So you have to consider all of that, and that messes with your timings, of course. If you don't use a core, it's going to take some time for it to wake up. So that's a very complex setup these days, and I wish there was a way to configure it for more accurate measurements.
No, I totally agree. Like if you're trying to measure the improvement that your optimization makes, then it's very important to get a sensible baseline that is always consistent, or at least consistent enough. It's very annoying when you make some changes. It's like, it's a little bit faster, but is it faster because it's actually faster, or because some other factor that I don't know about actually made it faster? And like the further you get down into what you're optimizing, the harder it gets. Like if you're optimizing at the microsecond level, then any kind of fluctuation is very very annoying to deal with, because it's 2 microseconds faster. Is that because it's faster, or because I just happen to be lucky this run? But like the higher up you go, like if you're measuring in hours or minutes or seconds, then this kind of inconsistency matters less, because it's just like the resolution is too high for those kinds of things to matter, I think. But it's it would be nice if there was something for that.
All right. Then, any closing remarks? Gentlemen, do you want to say something in the end? First of all, we should do the shout out for Superluminal. Can you tell us where can people follow the work and check out Superluminal, Ritesh?
So our website is superluminal.eu, because the .com was taken when we started the company. And we are on all social media, so Twitter, Blue Sky, and Mastodon. You can find them on the website, so it's easier to just go there than me spelling it out. Try it out. I think you'll like it.
And Dennis, your blog, do you have, maybe you can, if you want to put out the profiler, the instrumentation profiler, if it's tiny, then maybe it would be interesting to also showcase it.
I can't put the profiler, since I sold it. it later became telemetry for RAD game tools. But I do have, I think I'm linking a movie clip from it on my homepage. So if you go to voxagon.se, you can read, you can look at the video from it. I'm also on Twitter, Voxagon Labs. That's where I'm the most.
And Voxagon.se has also awesome blog. I love the blog posts there. So if anyone would like more technical content as well, like even more technical, I'm not saying that this discussion wasn't technical. It's like more technical in the like amounts. It's also there in the readable form on Danny's blog post. All right. Thank you everyone who tuned in and stayed with us and asked questions. Thank you, fine gentlemen, for joining me for the discussion. Please stay in the call
is to make sure that the video will be uploaded. Don't like turn off the browser. And yeah, thank you so much.
Yeah, thank you. And
Thank you too.
nice
Thanks
to talk to you,
inviting
Ritesh.
us. It was a pleasure.
All right.
Yeah, you too, man.